Hello, my name is Dr. John Polansky. I'm an assistant professor at the Kyushu Institute of Technology in Kitakyushu, Japan. And I'd like to talk a little bit about the laboratory that I work in. This is the Laboratory of Spacecraft Environmental Interaction Engineering, also known as LaSEINE. And it's a laboratory here at Kyutech. And the director of this laboratory, who started it in 2004, is Professor Meng Cho, and I've been working here at Kyutech for 1 year. So what I'd like to do today is talk about what we do and show you some of the chambers that we have. What we do in general is we try to simulate the space environment, and that can be from a plasma standpoint, it can be from a vibration standpoint during launch. There are many factors, but this laboratory in particular focuses on the plasma and in some ways the radiation environment in space. So let's go into the laboratory and have a look around at some of our chambers. So when we think about space, we know that there are many different orbits that satellites or objects can be in. And generally speaking, we talk about 3 different orbital locations: low Earth orbit, or LEO, polar Earth orbit, or PEO, and geostationary Earth orbit, geostationary or geosynchronous Earth orbit, or GEO. So what I'd like to do is start with those 3 chambers. Those 3 chambers are all infrastructure here that we use to simulate the space environment. So let's take a walk through the laboratory over to the LEO chamber to start with. And you can probably see there are many chambers and materials in this laboratory. Everything here is designed to help us simulate the space environment and to simulate satellites and objects that go inside the space environment for testing. So, if we progress down here, we see the LEO chamber, and maybe the best look is here inside. Oh, okay. So we can start here at the control area, and actually, this is kind of useful. I don't know if it's possible to see this, but this sketch shows the 3 different orbits that we're talking about. So right now it's the blue one. This is LEO, or low Earth orbit. Generally speaking, the altitude above Earth's surface is about 200 to 1,000 kilometers. This is where the ISS flies. The ISS is at an altitude of about 400 kilometers, and what's also interesting is that the inclination in LEO is usually fairly low. For example, the ISS is at about 51.5 degrees inclination. One of the reasons for that is, of course, coverage of the Earth, but also the Van Allen radiation belts. In LEO, we generally try to keep the spacecraft inside the inner radiation belt, but also above and below it. The radiation belt tends to terminate near the polar regions, or in the northern and southern latitudes. So this is the environment that we tried to simulate here. And what are some of the characteristics of the plasma? So maybe we should start by saying that the Earth is protected from the solar wind by the magnetosphere. The Earth is a molten rotating core, and that rotating core generates the magnetosphere. It protects us from the solar wind, and we have this complicated magnetosphere that forms around the Earth. In LEO, we're relatively protected from the solar wind, which means that we have a fairly low temperature or low energy plasma, and also fairly high it's fairly high density. Oxygen is one of the primary constituents. Oxygen is ionized by photoelectrons from the sun. Oxygen is ionized by UV light from the sun, and we get photoelectrons. So here we can take a look at, before we look at the chamber, we can look at some of the specifications. So this is the LEO chamber, and we see the size here. The diameter is about 1 meter. The length is about 1.2 meters. This chamber uses a mechanical roughing pump and a turbomolecular pump to reach its ultimate vacuum of about 1 × 10⁻⁴ Pascal. Here you can see a turbomolecular pump plus a mechanical rotary pump. And what do we use to generate the plasma? Well, because of what I mentioned before, LEO being a fairly low energy, high density environment, we use a plasma source, an ECR plasma source, and we can use different gases with this source, xenon, oxygen, for example. And what we try to do is generate a thermal plasma, where the thermal energy is much greater than the flow velocity. The thermal velocity is much greater than the flow velocity of the electrons. That's the type of plasma environment that we're generating here, and you can see a representative density here. So we generate the plasma, and then what do we do? Well, in this chamber, we can do a number of things. For example, we have a cooling shroud. You can see that cooling shroud here. In space, as we go from through eclipse, from darkness to daylight, we have temperature extremes, and this allows us to simulate that using liquid nitrogen. We flow liquid nitrogen in, and liquid nitrogen comes out, and it evaporates into gas in the room temperature. But inside the chamber, we can reach very low temperatures and thermally cycle, in some cases, our payload, which could be a solar cell or something else. Additionally, we have installed a lamp that we use to simulate the sun inside this chamber. So if we put a solar cell inside, for example, we can have some temperature control and also a solar simulator to introduce some IV curve to measure solar cell performance. So here we see the chamber itself, and I believe the chamber is actually under vacuum, so I don't think we can open it, but this is a mid-sized chamber, 1 meter in diameter, as I mentioned before, with a number of access ports. The plasma source is actually in the rear of this chamber, so it's hard to see from here, but we could perhaps take a walk around. To get a look at the chamber, one of the gate valves that goes to the pumping. And here is the actual source. This is an ECR plasma source. So we use, if we want to generate a plasma, we need to ionize a gas or accelerate a charged particle. In this case, we are ionizing neutral gas. For example, this bottle is our gas supply. And in this case, we ionize it with resonance from some microwave. We have a microwave generator here to ionize the neutral gas, and then we create a plasma. In this chamber, we unlike in the other chambers, which I'll talk about soon, we don't have the high energy plasma, so it's mostly just generating the plasma and using thermal motion, thermal energy, to simulate the space environment. And for the most part, that is what we do with this chamber. Of course, we have many diagnostic equipment. We have many diagnostic tools and equipment to not only measure the plasma, like a Langmuir probe, for example, but also to capture waveforms of experiments that are taking place, like this oscilloscope. And if you're watching this and you'd like more information, you may certainly contact me or anyone here at Kyutech or LaSEINE to get specific details on this chamber. This one, I think, is for temperature control, but I don't know if it's with that or not. So next, let's go over to the PEO chamber, the Polar Earth Orbit chamber. So similarly, we can take a look at the orbital sketch. So before we were talking about this inner orbit, but now we're talking about polar orbit. So polar means that the satellite is generally over the polar regions during its orbit, over the North Pole and South Pole. The altitude is generally between 500 and 1,000 kilometers. And this type of orbit, of course, can be used for a number of different applications. One popular application is to be in a sun-synchronous orbit. A sun-synchronous orbit has a regression of nodes that matches the Earth's revolution rate around the sun. And at a certain altitude and inclination, it's a dual variable equation, at a certain altitude and inclination, which is around 1,000 kilometers and 96 or 97 degrees, we have a sun-synchronous orbit. So that's one application for a PEO orbit. That being said, in polar Earth orbit compared to low Earth orbit, the plasma environment and the radiation environment can be quite different. In some ways it's similar. The thermal electron, the thermal plasma population that I described before, in some ways is similar in PEO. Relatively high density, relatively low energy, and fairly stable. But unlike LEO, in PEO, we can have aurora electrons, a lower density, higher energy, more variable plasma species or subset of plasma species that can greatly and drastically affect satellites through charging or voltage breakdowns or other negative effects. So what does that mean for us on the ground? That means that we have to simulate either independently or in parallel those two plasma populations. So in this chamber, we can take a look at, we'll walk into the chamber shortly, but we can take a look at the setup. Here we see the chamber and the interior, but if we look at the specifications, we see in some ways it's very similar to LEO, same size, same pumping system and ultimate vacuum, but one of the major differences here, and this is a very state-of-the-art chamber, is that we have both a high energy electron source. We have an electron beam gun that's capable of energies up to 30 keV, and we have a plasma source, ECR type, similar to the one over there, that can generate the thermal plasma population in parallel. Because we have such a high energy plasma in the case of the aurora electrons, which can be trapped in the polar regions by the magnetic field lines that terminate in the North and South Pole, because we're simulating such a high energy plasma, we also need to be able to measure the potentials that result on our experimental surfaces, which simulate satellite surfaces. So we also have diagnostic equipment that's capable of doing that. For example, Trek probes that can measure on the kilovolt scale and other diagnostic equipment. So this is the control area. We have a number of source meters and control mechanisms here. Let's see what program is on here. It could be from recent experiments. So here, for example, we see what would come out if we did a scan to get the potential. If we do some measurements, we charge some plasma, we charge some object with plasma. In many cases, we want to know the resultant potential. And this program would allow us to do that. We might have a surface with insulators, conductors, various materials. We charge it, and we use the Trek probe to scan the surface, usually in 2 dimensions, to obtain some surface potential field. And here, for example, we see the Trek probe controller. So this actually, a Trek probe is kind of an interesting device. There's the probe itself, which has a vibrating head that approaches the potential of the object that it's close to, but the underlying principle is to use an electrostatic voltmeter, an ESVM, to achieve that. So this is the ESVM, and the probe itself is inside the chamber, close to the sample. And the rest of this is a control panel for the chamber, operating the pumps. We get a readout on the pressure, etc. Now we can actually look at some of the really interesting equipment around the chamber. So similarly to the LEO chamber, we have a cooling shroud. It's a slightly different geometry, but the same idea. We want to be able to simulate the low temperatures in space, and in this case using cryogenic liquid nitrogen. So this can be moved in and out of the chamber. It's carefully designed, specially designed to go in and out of this chamber. So that's one aspect that's the same as LEO. The other aspect that's the same as LEO is the ECR plasma source for the thermal plasma, but the electron gun here located at the top of the chamber gives us very high electron energies if necessary. This is the feed through for the Trek probe, and we have a number of other components. This is where the liquid nitrogen would go in and out if it were installed, and we have a number of other components that can be used depending on the choice of experiment or the desired experimental setup. So you can probably hear some of the pumps operating. This chamber is under vacuum right now. I think some experiments were just taking place where surfaces were being charged to a relatively high potential and then exposed to plasma, or we just tracked charge decay over time, which can happen in space. So again, like I said, for the LEO chamber, if there are any questions about the PEO chamber, please contact me. My information will accompany this video. And now let's go over to the GEO chamber, the geostationary chamber. So let's take a look again at the orbital sketch. Now we're out at an altitude of about 36,000 kilometers. And I think everyone knows, we know, or we can quickly calculate from orbital mechanics that the semi-major axis of a geosynchronous orbit is 42,164 kilometers, which means we have a period of one sidereal day, slightly less than 24 hours to match Earth's rotation. And we have a various control software here. For example, this is the control program again for the Trek probe to get a surface potential distribution. And if we look closely, we can actually see an example plot that shows the resolution of the meter. This is at X in centimeters, Y in centimeters. So we have different data points that allows the program to interpolate some field based on the results. I don't know if this is real data or just a test to characterize the system. And this is the controller for the Trek probe. So, what type of missions are in GEO? Why do we care about GEO? Why are we trying to simulate it? Well, geosynchronous and geostationary orbit are very... geostationary orbit is a geosynchronous orbit with an eccentricity of almost zero, which means that the satellite stays over one place, one area on Earth. So in some ways advantageous to geosynchronous. But this is an ideal location for communication satellites, for television satellites, and many other large satellites. And this is a much more extreme plasma and radiation environment. Before I talked about the Van Allen radiation belts, the inner belt is just outside of LEO, which I described before. But the outer belt is actually primarily just inside GEO. So in this region and this region, there's a fairly large, intense radiation belt. GEO, like I said, is just on the fringe of that, but that radiation belt is highly variable and highly susceptible to geomagnetic storms, solar flares, etc., etc. So the particle energy that a geosatellite might encounter could be, in extreme cases, on the mega EV scale. So in this case, we want to simulate those very high energies. That's the primary purpose here in this chamber. And we do that with an electron beam gun. So we have a 30 keV gun, maximum current density, 300 microamps. And this plasma source actually was removed, so the plasma source is not present at this point. But we have the option of using a Kaufman type plasma source in really any of the chambers that we see here. So if for example, we wanted to also have high energy ions, or at least flowing ions, we could generate those with a Kaufman style source where we accelerate ions instead of just accelerating electrons. Previously we were talking about thermal plasma. Well, the Kaufman source will generate a mesothermal plasma where we have thermal electrons but flowing ions. So that's one capability of this chamber. And we can take a look at some of the equipment. We immediately see that this chamber is much smaller, and we see the electron beam gone here. And for all of these chambers, or whenever we're using an electron beam, we can shutter that beam. So, very loud noise from this pump. So the audio might be a little blurred here, but in any electron beam experiment, we may want to very quickly shut the beam off, turn the beam on, turn the beam on, and to turn the electron gun on and off is an intensive process, so we just shutter the beam with some shield on and off, for example. And we can walk around in the back of this chamber. We see some diagnostic equipment. And here we actually see a sub-chamber. So this is a small experimental chamber that's attached to the GEO chamber, so we can use the same pumping system for a separate set of experiments. It could be one thing or the other. I'm not actually sure what is taking place in here at the moment. So this is the GEO chamber, more or less. This is the geostationary chamber. So next, let's look at some auxiliary chambers. Those are the three core chambers: LEO, GEO, PEO. Let's look at some auxiliary chambers that allow us to simulate other aspects of the space environment. And we'll start in this corner over here. I guess before we go to the chambers, we can take a look at this one. We have here a solar simulator. So if we don't necessarily need a plasma environment or a vacuum environment to test our solar cells, but we do need a solar spectrum, a spectrum that at least simulates the solar spectrum. So we can do that with this lamp. And you can see here that light will be reflected from this lamp in a certain way, and this is very bright, and we need visual protection when using this system, but somewhat straightforward. So now we can talk about some of the auxiliary chambers that I mentioned. So let's start with the atomic oxygen chamber. As I mentioned before, when talking about LEO, in low Earth orbit, one of the primary plasma constituents is oxygen, because oxygen, particularly atomic oxygen, not diatomic, around Earth's surface, oxygen, nitrogen, and a few other molecules are diatomic, found in pairs in nature, but in the exosphere, above the four main layers of the atmosphere, we have atomic oxygen. This oxygen is photoionized by solar energy, UV energy from the sun, and this atomic oxygen is very chemically reactive, so and can cause harm and degradation to satellite materials and other objects in space. So what we want to do here is generate atomic oxygen at a certain velocity, a certain energy. We see that here, that represents the low Earth orbit environment. And to do so, we use a laser. Here we have a CO2 laser source. That's what we use to generate this plasma, this atomic oxygen. We use a mass spectrometer to make sure that we actually have what we want. And then we have a number of diagnostic equipment.